Hi. This clip provides an intuitive but admittedly quite simplified view of the nature of excitonic insulators. Based on this, I will describe how we monitor the recovery dynamics of an exciton condensate in real time. Photoexcitation of most semiconductors across their bandgap leads to the formation of bound pairs of electrons and holes, so-called excitons. Excitonic insulators are special materials, usually with a small bandgap combined with a large exciton binding energy due to low dielectric screening. When the binding energy exceeds the size of the bandgap, it is more favorable for the system to form excitons than to keep the electrons at the top of the valence band. Spontaneous exciton formation occurs in order to minimize the energy of the material. This happens by the formation of an exciton condensate. As a consequence, the bandgap widens compared to the semiconducting state and exhibits the characteristic flat top valence band. The material becomes an excitonic insulator. Intuitively, this process can be understood in the following simplified picture of a balance. The ground state of a semiconductor is a reservoir of electrons. Photoexcitation removes electrons from this reservoir that then may funnel back or funnel into the excitonic state. Depending on the exciton potential, this state will lie at higher or lower energies. In a ground state excitonic insulator, the exciton level lies below the surface of the reservoir if it were filled with all available electrons. Now, electrons are of course no water drops, and quantum effects like tunneling can occur in such a system. Electrons leave the reservoir and become part of the exciton condensate until the free energy is minimized and equilibrium is reached. The excitonic insulator is stabilized. As you might imagine, it is not easy to access these processes experimentally. We do this by using a trick. With a first femtosecond laser pulse, we drive an excitonic insulator, tantalum nickel selenide, out of equilibrium and monitor the electron relaxation dynamics using time and angle resolved photoelectron spectroscopy with a second laser pulse. We find that, after photoexcitation, the electrons do not return to the exciton condensate directly, but that they take a detour via the main reservoir, the valence band. They reach it after roughly a picosecond. Once they have arrived there, it takes few to 60 picoseconds for the exciton condensate to stabilize. The exact time constant of this process depends on several site conditions: the sample temperature and excitation density, which means the number of excited electrons in the laser spot. The reason is that the quantum tunneling may occur into both directions, forward and backward, and is thermally activated.